In our last video, we moved from discussion of what a function is to how it behaves. We introduced the idea of an injective function to describe functions that map elements so that there are no collisions. This video is going to introduce a similar idea that focuses on the codomain. So earlier we distinguished between the codomain of a function and its range. The codomain is a set that contains the outputs of a function, while the range is the set of actual outputs of a function. As this diagram shows, sometimes the range of a function is smaller than and not equal to its codomain. You can think of the codomain of a function as the data type of its outputs, while the range is the list of actual outputs. The outputs must belong to the codomain. They must be of a data type belonging to this set, but not every point in the codomain may actually get output. But sometimes the range and codomain are equal, like you see in this diagram. Here, every element of the codomain that can be hit by the mapping is hit by the mapping. This function is not injective because you can see a collision here, but it does have the property that the codomain and range are equal sets. These functions where the codomain and range are equal sets we will call surjective. More formally, if f is a function from a to b, note b here is the codomain, then f is said to be surjective if the following double quantified statement is true. For every point b in the codomain, there exists a point a in the domain such that f of a equals b. So this function from the previous slide is surjective because if you loop through each of the 4 points in the codomain, you can always find at least one, sometimes more than one, point in the domain that maps to it. But in the function from 2 slides ago, that's not surjective, because not all of the points in the codomain have at least one element of the domain mapping onto them. As you can see, these 2 points have no elements mapping to them. Here are some more examples of functions that are surjective and some that are not surjective. Here are 2 functions, one called f and the other g, both from the set 1, 2, 3, 4 to the set x, y, z, t. The first one, f, is surjective because, again, every point in the codomain has at least one point in the domain mapping to it. The entire codomain is covered by this function. In fact, that's where the word surjective comes from. It uses the French word sur, which means on top of. So a surjective function puts outputs on top of the entire codomain and doesn't leave any out. The function on the right, on the other hand, uses the same domain and codomain, but a different rule of assignment. And this one is not surjective because there's a point in the codomain that does not have anything mapping onto it. The codomain is not covered. Predicates are functions whose codomain is always the set of Boolean values true-false. The predicate p on the left has a domain equal to the set of natural numbers and assigns truth values using the statement n is even. This predicate, thought of as a function, is surjective because for each of the 2 values in the codomain, true-false, there's at least one input that maps to it. In fact, there are infinitely many points that map to each point in the codomain. Namely, all the evens map to true and all the odds map to false. The predicate q on the right, on the other hand, also has a domain equal to the natural numbers, but the rule of assignment is different. It uses the statement 2n plus 1 is odd. Now this statement is true for all natural numbers, so the only element of the codomain that's hit by this function is the value true. Nothing maps to false. That makes this function not surjective. So one application of surjectivity is that it's a way of describing a predicate that is always true, or one that is always false, but does not have both true and false values. What happens if the codomain is an infinite set? Well, let's take a look. This function f has a domain and a codomain equal to the set of real numbers, and it's defined by the formula f of x equals x squared plus 1. This function is not surjective because not all points in the codomain, which is the entire set of real numbers, have something mapping to it. In fact, nothing maps to 0 because x squared is always bigger than or equal to 0, and so x squared plus 1 is always strictly bigger than 0. So 0 is never hit, and so are a lot of other real numbers. In fact, we can visually see this if we use a graphing calculator. Graphing this function shows that there's a lot of points on the y-axis that have no point of reference on the graph. So that's a visual cue that this function is not surjective. But the function g from the real numbers to the real numbers, given by the formula g of x equals 2x plus 3, is surjective. To explain this, we need to explain why every point in the codomain has at least one element of the domain mapping to it. Since that's a universal statement about an infinite set, an example will not constitute a complete explanation. But it doesn't hurt to play with some examples first. So let's suppose I just picked out the number 2 out of the codomain. What maps to it? Well, it would have to be some real number x, such that 2x plus 3 equals 2. Well, when you phrase it like that, I think I can find that x value. Solving this equation gives me 2x equals -1, and so x equals -1/2. That's the point I would have to plug in to get 2 as an output. Now that's just one example, and so it's not a convincing explanation, but I think I can use this example to make a convincing explanation that does not have any specific values used. Pick any point out of the codomain, and just call it b. Can I find a point that maps to b? Well, it would have to be a real number, x, out of the domain, such that f of x equals b. The formula for f tells me this would mean that 2x plus 3 equals b. I can now solve that equation and get 2x equals b minus 3, and so x is equal to b minus 3 divided by 2. Now that shows me that for any b in the codomain, I can get a generic process for finding the value in the domain that maps to it. And that makes this function surjective. So in this video, you've learned about surjective functions and how they're defined. You've seen several examples of surjective and non-surjective functions, and we've looked at how to show in a convincing way why a function is or is not surjective. In our next video, we'll look at functions that have different combinations of being injective and being surjective.